Okay, let's go ahead and get started then. So the first thing here we're going to talk today, it's going to be a little bit of review. We're going to talk about graph of a linear function. And the graph of a linear function is a function whose graph is a straight line. All right, so that's what a linear function is. There are three forms in which we'll see a linear function. The first one here is like this ax plus by plus c, so it's like everything's on one side of the equation equals 0. Sometimes you might also see like ax plus by equals c. That's okay as well. Either one of those forms. But that is called standard form. All right. That's the first form that we see, standard form. The second form that you could see is this one where it has like y minus y1 equals m times x minus x1. And this is called point slope form. And it's called point slope form because you have this x1, y1 here. That's technically an ordered pair. So that's like the point. That's why it's called point slope form, because it gives you a point on the line. X1, Y1 would be a point that's going to be located on the line somewhere. And then the other thing it gives you is this m. Does anyone remember what the m stands for in these linear functions? It's in both of these last two equations.
The growth.
The what?
The growth.
The growth, yeah. So it's going to be specifically the growth, the change, the rate of change, and we also call it the slope. So I'm going to use the word slope here, but yeah, growth is the right idea. So that's the slope. So that's why this is called point slope form, because it gives you a point on the line. It also gives you the slope of the line. Okay? So that's the idea. So that's where point slope form comes in. The last one here is called slope intercept form. All right, and this one also, again, it's called slope intercept because it tells you the slope just by looking at it. But then it also tells you an intercept. Does anyone know what intercept it's telling you? That's what this b value is. Yes, exactly. That's the y-intercept. You got it. So that's why it's called slope-intercept form. So standard form, not really useful at all. It's just, hey, sometimes we have the x and the y on the same side of the equation. Point slope form tells you point and the slope, which is awesome. You get 1 point on the line and the slope of the line. Slope intercept form tells you the slope and the y-intercept. And although there are three different forms, the simplest one to graph is generally slope intercept form. You can graph point slope form as well, but I think slope intercept is a little easier because you know one of your first point is going to be on the y-intercept. All right. But in order to graph slope intercept form, the first thing we need to be able to do is rewrite each equation in slope-intercept form. And whenever it says rewrite in slope-intercept form, that's just a fancy way of saying solve for y. You want to get y by itself on one side of the equation because that y equals mx plus b. So on this first equation, I'm going to zoom in on part A here. We're going to go ahead and start by saying let's add 12 to both sides. So now I have x plus 3y equals 12. 0 plus 12 is 12, and then negative 12 plus 12 is 0. I don't need to write 0 anymore, so I just have x plus 3y equals 12. Next, I want to subtract x from both sides. And just to keep it in that slope-intercept form, that like y equals mx plus b, I'm going to write this as negative x plus 12. Excuse me. And then the last step, I'm going to divide both sides by 3. And that means divide everything by 3. I'm not just dividing x by 3. I'm not just dividing 12 by 3. I'm dividing both sides by 3. So, for example, 3 divided by 3 is 1. I'm going to be left with y. On the other side, I'm going to have negative x over 3 plus 12 over 3. Divide both parts by 3. And then the last step here, I'm going to write y equals, so I could write it as negative x over 3, but that can be a little bit confusing. So the way I'm going to write it instead is negative 1/3 times x. And then 12 divided by 3 happens to be 4. So that's how I'll write part A here. So negative 1/3 x plus 4. Okay, that's a good way to write it. And the reason is because slope is the m value. And what happens is sometimes people see something like this, negative x over 3. And they say, oh, the slope is negative x over 3. But x isn't part of the slope. It's m times x. So the slope is just this negative 1/3 here. That's why we write it like that with the negative 1/3 times x. Because negative x over 3, you can always say that there's a 1 times x. So that's what we're doing there. We're just showing that the 1's there. Okay, even though it doesn't have to be written explicitly. Okay, that's the first example, example A. Example B, we want to solve for y. Before I solve for y, I got to get rid of these parentheses. So I'm going to distribute this 2 to both sides of the equation. So I say y minus 4 equals 2x plus 6. All right. And just remember, distributive property says I multiply the 2 by everything in the parentheses, and then I'll get rid of the parentheses. And then the last part, to get y by itself, I'm going to add 4 to both sides. So I end up getting y equals 2x plus 10. I just have 6 plus 4 there, so I get y equals 2x plus 10. All right, so that's what part B looks like. That's how I would write down my 2 equations in slope-intercept form. And I'll go ahead and box them both up here. All right. So the next part, once we have this written in slope-intercept form, I'm going to show you an example to graph this function in slope-intercept form, and then I'll give you guys a minute to work on the second example here. So the first thing first, if we have the equation written in slope-intercept form, start by identifying the slope and the y-intercept. So from example A, the slope was at negative 1/3. That's why we want to split it up. And the y-intercept is 0, 4. And I'm going to write it as an ordered pair. So that way I know the y-intercept is on the y-axis, 0 is the x value. So 0, 4. So it's going to be on that vertical axis. The second thing I want to do is I'm going to plot the y-intercept, and I'm going to use my slope to count every point that falls on my scaled axes. In the scaled axes, that's going to be how I number my grid. That's really important. Sometimes you might create a scaled axis and then you realize it's not going to work, so you have to change the scale. It's basically our viewing window. Like if we did this on a calculator, it's how we view the graph. And for this problem, I'll scale my axes by counting by 1s in the x direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But I don't need to write a number at every single point. As long as I put a scale like every 5 or so, all right, that would work. And that's what I'm doing here. And then in the negative x direction, I'm going to go -5 to -10. And then for the y direction, I can count by 1s as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we'll go -5, -10. So that's important. That's what the scaled axis means. Okay, next step, it says I need to plot the y-intercept, which is 0, 4, 0, 1, 2, 3, 4. Plot the slope, which is, use the slope to plot every point. So it says negative 1/3. And you guys might remember that the slope is also called this thing where we say rise over run. Rise means the y-axis, up and down. Run means the x-axis, left and right. So in this case, the rise you could say is -1, and the run is +3. Even though there's a negative, it only affects one of the numbers. So that means I go down 1, and then to the right 3. 1, 2, 3. Plot my next point. Down 1, right 3. 1, 2, 3. Rise over run. Down 1 over 3. 1, 2, 3. And if I go down 1 over 3, I'm going to be off the paper. So, off my grid, I should say. So I'm just going to leave it like that. And now I'm going to go in the other direction, except because only one of the numbers can be negative, I could say, like, I could go up 1 and then to the left 3, because I'd be in -3 direction. Up 1, left 3. And we'll see that they all fall on the same line as well. Up 1 over 3. Up 1 over 3. And then I'd be off the paper. So I have all of my points plotted that would cover my grid. And now I can sketch a line straight through all those points. All right. And the last part, I want you to do step 3 here. Algebraically solve for the x-intercept. And for example, on this one, the x-intercept, I can see it's not quite on my paper. It's going to be somewhere over here, just slightly off my paper. So like 11, 12, 13, somewhere in that area. So what I want to do to algebraically solve, show my work, I need to plug in 0 for y, because the x-intercept is going to be x comma 0. That's why I plug in 0 for y. So in this equation, I would say 0 equals -1/3 x plus 4. Okay, and what I'm going to do then is solve for x. I'll subtract 4 from both sides, and I get -4 equals -1/3 times x. And I want to get rid of that -1/3, so I'm going to multiply by the reciprocal of -1/3. Okay, and the reciprocal of -1/3, do you guys remember what a reciprocal is? Where you take a fraction and you flip it over. So the reciprocal is going to be -3 over 1. I'm going to multiply both sides by -3 over 1. And what's really happening here on the left side, it's like -3 over 1 times, we could say -4 over 1. You could kind of think of the 4 as just over 1. And you're just multiplying straight across. -3 times -4 is positive 12. 1 times 1 is 1, so it's 12 over 1. So you end up getting x equals 12 over here. So your x-intercept is 12 comma 0. That's how we'd algebraically prove it. And like I said, on the graph, it looked like it was going to be around 11, 12, 13. So that checks out. That means we did it correctly. If I got something like -5 for the x-intercept, and it doesn't look like it's anywhere on near the line, then that'd be a bit of a problem for us. But in this case, it looks like it worked out, so that's how I know I did it correctly. All right, that's how you graph a linear function. Now I want you guys to practice on example B, so take a minute and practice that. I'm going to check the chat for questions and answer any questions people might have had. Okay, so let me know if you have any questions at all. Okay, so for example B, algebraically we can solve for the x-intercept and we get -5 comma 0. But this one's a little different because this time I have the y-intercept as 0 comma 10, so I know where to put that on my graph. I just did a scale of 1, by the way, in all directions. but my slope is 2. So the first time, at least, it was rise over run, so it was real easy to do the fraction and count. How would I count this time using a slope of 2 if the slope's an integer value?
Most of the time you would just go over 1 and then up 2.
Yeah, exactly. So this time you can think about it as like 2 over 1. So the rise is 2, the run is 1. So again, just because 2 is the same as 2 divided by 1. So yeah, if I go up 2 and to the right 1, I'd be off the paper, so that's not going to work very well. So instead I'll just go down 2 and to the left 1. Down 2 to the left 1. Down 2, left 1. Down 2, left 1. And thankfully I hit -5, 0 as I'm doing that as well. And then I'm going to keep going down 2, left 1 until I'm off the paper. There we go. And yeah, my first point was not very accurate when I went up and to the right. Come on. No one let me erase that point. Whatever, we'll do that. Okay. So that's how we would end up graphing this particular point. So now we've got our line sketched for this one. We found the x-intercept and we proved that it's correct. That's graphing linear functions. All right, a little bit of review there. Hopefully that's not too bad for us, the graphing linear functions. Solving for x-intercepts, plugging 0 for y. All right, getting into slope-intercept form. All right, that's some old AGS1 stuff there. Now we're going to take a trip down AGS2 lane. This is graphing a quadratic function in vertex form. Now, quadratics had 3 forms as well. We had standard form, which was like that ax squared plus bx plus c equals 0. We had intercept form, which was like 0 equals a times x minus p times x minus q. And then we had vertex form, which is this one right here. Y equals a times x minus h squared, quantity squared plus k. And we're going to graph in all 3 forms, but right now we're just going to focus on vertex form today. We're going to talk about the other forms tomorrow. And you might remember vertex form, the vertex was h comma k. So it's just these values here, h comma k. H was always the opposite of whatever the sign was in the parentheses. K is just going to be whatever is being added outside the parentheses. The axis of symmetry was always just going to be the x value of the vertex. And the axis of symmetry cuts the parabola in half. So it cuts it perfectly in half vertically and you're mirrored on both sides. That's what the axis of symmetry was really good for. All right. The parabola opens up if the a value is positive and opens down if the a value is negative. And in all right, so that's the idea. So it opens up if the a value is positive, down if the a value is negative. That's some important things to remember about vertex form quadratics. And again, the axis of symmetry would be what cuts the line perfectly in half, or what cuts the parabola perfectly in half. And we'd say x equals h. That's how we'd represent it on a graph, just by drawing a dashed line right up the middle. Okay, through the vertex. All right, so let's go ahead and graph one. We'll practice graphing a quadratic in vertex form. First things first, I want to identify and sketch the axis of symmetry. And in this case, y equals a times x minus 2 squared minus 1. There's no a value, so it's safe to assume that's going to be a. positive 1. So we can say A is positive 1 here. So that means it's going to be opening up. We know that. All right, so if there's not a number there, it's just 1. Okay, axis of symmetry, x minus 2. So the axis of symmetry is x equals 2. So we can identify that and we can sketch it on our graph. Before we can sketch anything on our graph, we're going to need to put our scale on here. I'm going to go ahead and scale the x-axis by 1s, and I'll scale the y-axis by 1s for this example.
Wait, why is the x-axis 2, or the axis of symmetry?
The axis of symmetry is 2 because it's the number that's inside the parentheses here. So it's always the opposite sign of what's actually in the parentheses.
Never mind.
Yep. So that's why it's 2. So I'm going to draw a vertical line here. X equals 2. And go ahead and label it. And then I'm going to identify and sketch my vertex. 2 is the x value because this should be the same as the axis of symmetry. And then we had a minus 1. So that's the y value. 2 comma negative 1. 2 comma negative 1. Perfect. It falls on the axis of symmetry. That's what I like to see. Okay. Now I want to solve for the x-intercepts and the y-intercept. Sure. Sorry, we're going a little fast, huh? Sorry, going a little too fast. Slow down a little bit. So, yeah, what I want to do next is solve for the x-intercepts and the y-intercept. So what we're going to be doing then, to solve for the x-intercept, we do exactly what we did before. We plug in 0 for y. And to solve for the y-intercept, we're going to plug in 0 for x. That's the idea there. Okay. So I'm going to zoom in a little bit here. X-intercept. Plug in 0 for y. Y-intercept. Plug in 0 for x. Okay. And for the first one, when we're plugging in 0 for y, we just can rewrite it like this. 0 equals x minus 2 squared minus 1. We're plugging in 0 for x. All right, we're going to have a 0 plugged in right where the x value was. And this one 0 plugged in right where the y value was. So right off the bat, I can tell you y-intercept is going to be easier to solve than x-intercept. Okay, and that's when we plugged in 0 for x. Because now I have this, I'm just going to go through PEMDAS here. I have, inside the parentheses, I have 0 minus 2. Be left with negative 2. And then I do exponents. Negative 2 squared, that's if I multiplied negative 2 by itself twice. So negative times the negative is a positive. 2 times 2 is 4. And then last part is subtraction. 4 minus 1 is 3. So my y-intercept would be 0, 3. X-intercept. All right, I'm going to go ahead and start by adding 1 to both sides to try and get x by itself. So I get 1 equals x minus 2 squared. And then how do I undo a square? If I have a number squared, how do I undo that?
Root it.
Yeah, square root both sides. Exactly. You guys got it. Square root both sides. And when I square root both sides, I have to put a plus or minus in front of the square root on this side when I'm undoing a square. So on the right side, square root of x minus 2 squared is just x minus 2. On the left side, what's the square root of 1? Just 1. So I get plus or minus 1. And what I can do is I can write two separate equations. One of them is x minus 2 equals negative 1. One of them is x minus 2 equals positive 1. And now I'm going to solve each one for x, which makes sense. I should have two x-intercepts. And that's what's going on here. So I get negative 1 plus 2. That gets me a positive 1. And positive 1 plus 2 gets me a positive 3. So it turns out my x-intercepts are 1, comma 0 and 3, comma 0. And now that I have my x-intercepts, I can go ahead and plot those on my graph. Sorry, I'm going to give you guys a second to stay caught up there. I'll zoom out just a little bit. So I can plot those on my graph. 1, comma 0, 3, comma 0. Perfect. And then I'm going to plot my y-intercept 0, comma 3. So I've got 4 points now plotted on my graph. Step 4 says find other integer points and connect them with a smooth curve. Basically, I want to find a total of 5 points, including the vertex. So I have 4 out of 5 points. And the nice thing is, because I have the axis of symmetry sketched here, I know that there should be a mirror point on the other side of this y-intercept. Like the x-intercept has 1 at 1, comma 0. It's 1 unit away from the axis of symmetry. And then 3, comma 0 is also 1 unit away. So I can do the same thing here. I'm 2 units away. So if I go 2 more units to the other side, I'll find a point. So I can find a point at 4, comma 3. And that would be my 5th point. So now I have 5 points that can represent my graph. And I can go ahead and sketch it with 5 points. And then put my arrows on both sides of the quadratic to show that it goes on forever in both directions. All right, if I wanted to algebraically find the 5th point, I could plug in a 4, which is just saying, like, let's find the next point to the right. And that would work as well. It would verify that I get 2 squared minus 1, which is 4 minus 1, and I get y equals 3. So my point would be 4, comma 3 when I plugged in a 4 there. Okay, that's another way I could do it. All right, to find that 5th point. But I think, honestly, using the axis of symmetry and finding the mirror point is the best way to do that. Okay, now I got 3 practice problems for you guys here. I want you to identify and sketch the axis of symmetry and the vertex. Use algebra to find the x-intercepts and the y-intercepts. Okay, for each of these 3 problems. Round to the nearest 10th if necessary. Okay, so try those 3 problems out now. I'm going to give you guys about 10 minutes to work on those 3 problems, maybe a little bit more. They're kind of long. But that's the idea for this first point. Not sketched perfectly, but it should be directly on that axis of symmetry. Okay. For the second one, I ended up with like 2 minus square root 6, comma 0, and 2 plus square root 6, comma 0. Remember that we want to find exact answers when possible. And then we'll convert it into decimal for graphing. I didn't happen to have a graphing calculator on me, or a calculator on me, so I just left it as 2 minus root 6, 2 plus root 6. I know that 2 minus root 6 is going to be somewhere between 0 and 1, negative 1, and 2 plus root 6 is going to be somewhere between 4 and 5. So that's just kind of where I based my points on. I don't know the exact round to the nearest 10th answers. But if you can leave it in exact form and then turn it into decimal for the graph, that'd be awesome. All right, that's the best way to answer this type of problem. Okay, and then for the last one here, problem 3, it turns out that my vertex is also my only x-intercept. There's no other x-intercept. And my axis of symmetry is x equals negative 3 as well. So the The question here, though, is I only have 3 points, and I want at least 5 to plot. So I'm going to need to figure out at least like one other point. And the way I can figure out another point is I can go ahead and plug in a value. So for example, the axis of symmetry is at -3. I could plug in like -4 maybe, just go 1 unit near it. And that'll give me a -1 squared, which is 1. So now I've got a point that I can use. -4, 1. And that means -2, 1 would also be an equal point. And now I've got 5 points. I can go ahead and sketch my parabola there. All right, there was a question here. So for number 2, where did the 6 come from? So what happens is I started by setting my y equal to 0, and then I added 3 to both sides. And now I have 3 equals 1/2 times x minus 2. But I have to multiply by the reciprocal of 1/2, so I multiply everything by 2. And that's both sides of the equation. So I end up getting 6 here equals x minus 2 quantity squared. And then I can go ahead and square root. I'm just working backwards to try and get x by itself. That's where the 6 came from there. Okay, so that covers these 3 problems here. I did go through them a little fast. If it is a little confusing for you, just remember that we do have office hours today at 2:30. So just stay on the Zoom call and I can answer your questions right after class. But for right now, I just want to cover the last topic of the day, which is domain and range. So last thing today, domain and range. The way domain and range works is, first let's define them. Domain is basically it's the list. They're both lists. It's the list of all possible x values I can graph. Okay, so that's the list of all possible x values for the problem, for the equation. And the range is the list of all possible y values. All right. So we're going to work more on domain and range the next couple class periods as well. But this is the idea for domain and range. We're going to work on domain and range specifically in interval notation. So that's writing them as intervals. And domain, for example, all right, of a linear function, no matter what, if I went back and looked at a linear function like a line, you can see that this goes up and down forever on this line, and I have arrows that show that it goes on forever. So it means whatever number I plug in for x, I'm always going to get a y output. That's what domain and range would be. Oops, and then let's see here. Oops, okay, so scroll down. So for this one, any linear function, I can actually just say -infinity to +infinity. I can always go all real numbers on domain for this. All right, and we write parentheses and brackets when we're doing interval notation. You guys might remember this. You've seen it before, hopefully. And brackets mean that I'm including the number. Parentheses mean I'm not including that number. And with infinities, we always use parentheses. The range for a linear function is also always going to be all real numbers, -infinity to +infinity. That's always true for domain and range of any linear function, always. You can always say all real numbers and be correct. Or -infinity to +infinity and be correct. All right. With quadratic functions, like this example, x plus 4 squared minus 5, the domain is also always going to be all real numbers for any quadratic function. All right, any quadratic function domain will always be all real numbers. I can plug in any x I want and it's going to work. But there's a limit to what y could be. Right here, it only ends at whatever the vertex is. In this case, they're all pointing up, so the minimum value is the vertex, and then it goes up to positive infinity from there. So for this example, positive a value means it's pointing up. The vertex is -4 comma -5. So -5 is where the range is going to be. The range starts at -5, but it includes that number, and then it goes to positive infinity. And again, the brackets mean -5 is included. The parentheses mean not included. And again, we never include infinity or negative infinity, because I could say, oh, well, this goes to exactly infinity, and I put a bracket on there. You could say, well, what's infinity plus 1? So that's why we always just say not included. So you can keep going on infinities. All right, so that's the difference between a bracket and a parentheses, but that's how we'd write interval notation for these types of problems. We'll get a lot more practice with domain and range, don't worry. But for your...
Excuse me?
Yep.
Could you scroll back up to the graph for a second?
Sure, which one? This one?
The last one.
Sure,
The...
no problem. Okay, so